Hi guys, in today's video we're going to be talking about Newton's three laws of motion. Newton's three laws encapsulate important characteristics of the physics of forces and their connection to the motion of objects. It's important to note in this discussion that Newton was not responsible for all of the ideas that are encapsulated in his laws of motion. He was, however, the first person to bring them all together and to state them in this concise form. So to kick things off, let's start talking about Newton's first law. Newton's first law is often also referred to as the law of inertia. Newton's first law states that any body at rest will remain at rest, and any body in motion will remain in uniform motion in a straight line unless acted upon by an external unbalanced force. Now, there's several things going on in this description. First of all, the idea that a body at rest will stay at rest and a body in motion will remain in uniform motion in a straight line are both dealing with the idea of no acceleration. There can be no change in speed or direction of the object unless acted upon by an external unbalanced force. What this law implies is that the natural state of motion of any object is to continue its current motion. An object at rest will remain at rest. An object in motion will remain in motion unless forced to do something different. This was a fairly revolutionary view and actually came about as a result of experiments by Galileo. Before that, the prevailing view had been that the natural state of objects was at rest, that you only got motion when you forced an object to move, and that the second you took away that force, the object would slow down and stop. Think about pushing something along like a trolley. As long as you continue pushing it, it keeps moving. If you take your hands off and stop pushing, it will slow down and stop. This is a fairly intuitive and common example of motion in our everyday lives. And it's pretty easy to see why that was the prevailing view beforehand. What was important to realize, though, and it came from Galileo's experiments, is that there is often a force acting, and that is the force of friction between objects. It's possible to reduce the force of friction, and Galileo did this using oils and smooth surfaces, to the point where you can show that an object remains in fairly constant motion if you can eliminate that force of friction, thereby leading to the conclusion that if you could remove all forces from the object, including friction and air resistance, the object would continue in constant motion indefinitely. Of course, nowadays we're a little bit more open to this idea because we've seen a lot of depictions of motion in space. So we know that an object thrown out into space will continue moving forever. The problem is, down on Earth, everything is pulled down by gravity, which means inevitably objects interact with one another. If you roll a ball across a table, it's also pulled into the table by the force of gravity, which means there's then an interaction between the ball and the table. And this is something we'll explore a little bit more later. One thing it's important to note is that the law of inertia is often personified a great deal, so people talk about objects wanting to move in the same direction. Be very careful of these kind of descriptions, because while it is true to say that an object will remain in motion in a straight line at a constant speed unless forced to slow down or change direction, this is not something that they want to do. It's simply the laws of the universe. We'll now move on to talking about Newton's second law. Newton's first law was concerned with the idea that motion would remain unchanged unless acted upon by an external unbalanced force. The second law leads directly from this and asks, well, if there is an unbalanced external force, what will be the resulting change in motion? Newton's second law then is famously stated simply as F equals ma, an equation that relates the force applied to an object and the acceleration that it experiences. And the constant of proportionality in this case is the inertial mass of the object. Of course, technically, the equation shouldn't be stated in this form, it just is because it is neater. The real version of this equation should be written as acceleration equals force divided by mass, i.e. the acceleration is proportional to the force applied to the object and inversely proportional to the mass. So if you increase the force, you get increased acceleration. If you increase the mass, though, you decrease the amount of acceleration you get. The reason why this is more appropriately the form of the equation is that the force is the independent variable in most cases. We apply a force to an object, and the acceleration is what results. Putting this in words, we get that the acceleration of an object is proportional to the net force applied to it, the constant of proportionality being the inverse of the mass of the object. Now, there's one very important word in that sentence that I want to highlight, and that is net. In this formula, it is the resultant force on the object that matters. What this means is if you have two people pushing an object from opposite sides with equal force, there's going to be no acceleration because the two forces cancel one another out. It's the addition of all of the force vectors that results in the acceleration. And that brings us to the second point. This formula should be written as a vector formula. The force and acceleration are both vectors. So whatever the direction of the resultant force, the acceleration will be in the same direction, and its magnitude is related by this equation. Newton's third law is perhaps the most difficult one for people to understand. It is stated as whenever one object exerts a force on a second object, the second object exerts a force on the first object that is of equal magnitude and opposite direction. The problem with Newton's third law is that we often don't naturally see its effect. For example, when I push on an object, I'm not really feeling that the object is pushing me back. However, if I was to do this on some nearly frictionless surface, say in the middle of an ice pond, and I pushed an object away, I would go sliding back across the ice as well. If I had a rope connecting me to another object and I pulled it towards me, both the object and myself would end up sliding across the ice towards each other. It's only that we normally plant our feet or in some way act to counter that reactionary force that we don't end up noticing it. Newton's third law, of course, is a prime example of how rockets work. Rockets force material out of the base, and that pushes the rocket forwards. I've always personally liked to think of this law as forces come in pairs. Whenever two objects interact, they interact equally. If they pull one another, they are both pulled together. If they push one another, they both push each other. This works in all cases. For example, when the Earth and its gravity pulls us down, we actually pull the Earth up. So something dropping towards the Earth is actually pulling the Earth up towards it. Of course, the forces are equal in size, but according to the second law, the accelerations are proportional to the inverse of the mass. And since the Earth's mass is very, very large, the amount of acceleration that it experiences is incredibly tiny. So overall, it looks like one object is pulled down to the other, when in actual fact they are both pulled towards each other.